sklearnbase. Short description: this provides a concise overview of the class. Here, it describes the fundamental role of the sklearnbase class in scikit-learn, stating that it forms the foundation for all machine learning models within the library. Inputs. X. This represents the training data. Typically, this is a 2D array, also known as a matrix, where each row is a data point and each column represents a feature. Y. This represents the target values. These are the labels or outcomes you want to predict. It's usually a 1D array, where each element corresponds to the target value for each data point in X. Outputs. Self. This refers to the fitted estimator itself. After training on the data, the model stores learned parameters within this object. You'll use this fitted object to make predictions on new data. Predictions. Once the model is trained, you can feed it new data similar to the training data but unseen, and it will generate predicted target values. Fine-tune parameters. These are parameters that you can adjust to control the model's behavior and potentially improve its performance. Fit intercept determines if the model should calculate and intercept a constant term during training. This is often necessary for models that don't inherently pass through the origin 0 of the data space. Normalize controls, where the features in the input data should be scaled normalized to have similar ranges before fitting. This can be beneficial to prevent certain features from dominating the learning process due to vastly different scales. Copix decides whether the input data X should be copied before fitting. This can be useful to avoid unintended modification of the original data. Challenges and fixes. These highlight common problems encountered when building and training machine learning models and suggest potential solutions. Challenge 1. Overfitting. The model learns the training data too well, memorizing the specific patterns, and consequently performs poorly on unseen data. Related fix. Regularization techniques, e.g., L1 and L2 regularization. These techniques add a penalty term to the model's cost function during training. This discourages the model from assigning extremely large weights to individual features, preventing it from overfitting to noise in the training data. Challenge 2. Underfitting. The model is too simple to capture the underlying patterns in the data, leading to poor performance on both training and new data. Related fixes. Increasing model complexity. Consider using a model with more parameters, e.g., adding more hidden layers in a neural network to allow it to learn more complex relationships. Using a more expressive model. Explore different models that are known to be better suited for the type of data you are working with, e.g., switching from linear regression to a polynomial regression. Challenge 3. Data imbalance. One class in your data has significantly fewer samples than another. This can cause the model to favor the majority class and perform poorly on the minority class. Related fixes. Oversampling. Minority class. Replicate or create synthetic instances of the minority class to balance the dataset. Undersampling. Majority class. Reduce the number of instances in the majority class to balance the dataset. Using weighted loss functions. Assign higher weights to the minority class during training, so the model penalizes misclassifications of minority samples more heavily. Challenge 4. Missing values. Some data points have missing values for certain features. Related fixes. Imputing missing values. Replace missing values with estimated values, e.g., the mean or median of the feature. Removing samples with missing values. Delete data points that have missing values, but this can lead to information loss if too many samples are removed.